Okay, we shall start now. In today's tutorial, we do have 5 questions, and these questions are about analyzing piles with lateral loadings. So to find the ultimate lateral loading capacity of the piles at different scenarios. We're gonna assume the free head pile scenario, and we're gonna assume as well the fixed head pile scenario. And for both scenarios, we need to assume the short pile failure, the long pile failure, and for the fixed, we need to assume the short and the intermediate and the long pile failure scenarios. In each of these scenarios, the number of parameters or considerations which affects the ultimate lateral load will change. For example, in the case of the short pile failure scenario, the bending moments will not affect the ultimate load bearing capacity. The ultimate load bearing capacity in the case of the short pile failure scenario will only be affected by the dimension of the pile. But in the other case, the dimension of the pile and the soil as well. But on the other case, which is the long pile failure scenario, will be affected as well by the bending moments or the yielding stress of the pile material. Okay, so we're gonna start now with the first questions. In the first questions, we do have a 6 meter long pile, free head pile. So we have here a free head pile scenario, and L capital, which is the length of the pile, is 6 meter. That's embedded in a clay, which is a cohesive soil, homogeneous cohesive soil. So it's only one layer. And in all of these analytical solutions you have covered in your lecture, they only consider the simple scenario, which we have only one soil layer, and that soil layer is homogeneous, either clay soil, cohesive soil, or cohesionless soil. So in this case, we have a clay soil with cohesion of 50 kilopascal. This is the undrained shear strength of the soil. The outer diameter of the pile is 305 millimeter, and the wall thickness of the steel pile is 19 millimeter. That will help us to find the moment of inertia of the pile, the thickness of the pile. We're going to use it later to find the moment of inertia, I capital. We need to calculate the ultimate lateral load and bending moments. So we need to find H ultimate and M maximum or M ultimate. We need to assume the eccentricity of the horizontal load is 0.5 meter. We need to consider, to solve this question 1, we need to consider the short pile failure scenario. Assuming no axial load, we need to calculate as well the maximum stress developed in the pile. So after we calculate the bending moments, we can calculate the maximum stress. So we have here 3 things we need to find in these questions, which are the ultimate lateral load, the bending moments, the ultimate bending moments, and the maximum stress, stress on the pile. Okay, so to solve these questions, if you go back to your lecture notes, in this lecture notes, you have already derived all the necessary equations, but we're gonna review this one for a few minutes, just to make sure that you are following us in this tutorial. So for the first scenario, we have a free head pile in cohesive soil, and the pile head is free to rotate. So we have this scenario, and we have here the short pile failure scenario. So this is the scenario we are talking about. This is the short pile failure scenario. Okay, and in this case, we have the M maximum is less than My, the M yield. Hence, the rigid rotations ultimate, the maximum or the ultimate horizontal load depends on the pile geometry only and CU of the soil. But in the other case, it will depend on the my as well. So in this case, we have this scenario here. And as you can see, you have different forces in this problem. So you have the H ultimate, the unknown value we need to find out. And this is the reaction from the soil. This is the reaction from the soil. And as you can see, we can segment this reaction into 3 parts. So we have this part here, which is the one above the maximum stress point, or the zero shear force point, which is denoted by the F length here. And we have this one here, which is denoted by G over 2, and the last one here, which is G over 2. So we're going to have a number of equations. The equation you will have here, they are according to the static equilibrium rules or laws. The 2 equations, you're going to have one from the equilibrium of the horizontal forces in the problem. So you're going to have 1 equations, and you're going to have another equations from the sum of moments at certain point in the problem. So all these questions in this tutorial and on these subjects, they rely on the static equilibrium principles. And these principles give us 2 equations depending on the size of the problem, the domain of the problem. Here we are dealing with the 2-dimensional problem. In the 2-dimensional problem, we only have 2 equations, one coming from the sum of the horizontal forces, and the sum of the horizontal forces should be 0 on the systems. And by taking the moments at certain point on the system as well, either the rotational point or any other points. So you have the horizontal forces, you will have equation from the horizontal forces, and you will have another equation from the moments in the problem. Okay, so if we proceed with the solution here, so in this case, as we can see here, we have H ultimate. We have here the value of eccentricity, which is 0.5 meter. And we have the length of the pile as 6 meter. We have the underage shear strength of the soil as 50 kilopascal. And this is the dimension of the pile cross sections, which is the external dimensions, or the external diameter is 0.305. And we have the thickness as the shell thickness here is 19 millimeters. So you can work out what's the dimension of the internal area here, and that's to work out the moment of inertia. We will need that later to find the stress on the pile material. So for the short pile failure scenario, as we said, we have 2 equations, one coming from the sum of the horizontal forces on the systems, and sum of the horizontal force in the system. If we go back here, the sum of the horizontal forces on the system, we have H acting on that directions, on the right directions, and we have these forces, the distributed forces, the reaction from the soils, acting at different directions. So as we can see here, this force here, which is, maybe I can show you maybe another figure, maybe it will be more clear. Yeah, we have this figure. It's the same as the one you took in the lecture notes. So we have here the H ultimate, and we have here the reaction from the soil acting at different 2 directions. We have these forces acting on that directions to the left-hand side, and we have the one at the bottom acting to the right-hand side. So as you can see, the one within the length G, which is segmented into 2 parts, G over 2 and G over 2, the one, the top one and the bottom one, these 2 horizontal forces will cancel each other, because that one acting to the left and that one acting to the right. So these 2 forces here will cancel each other. So what we're gonna end up with, the sum of the horizontal forces will only be equivalent to HU, and that will be equivalent to the distributed forces within the length F here, the length F. The length F is up to the maximum moment point here. So we have the sum of the distributed force within the length F, and that will be equivalent to, within the length F will be equivalent to the 9 CUD multiplied by F. So we have here 9 CUD multiplied by F, that will be equivalent to the H ultimate. And that's the first equations in this problem. And as you can see, H ultimate is equivalent to the F, which is the length of the distributed force within that segment, within the top segment above the maximum moment point. And we have the 9 CUD, which is the amount of the distributed force on that sections. So we have, this is the first equation. So we have done it from the horizontal forces. Now we need to find another equations from the sum of the moments at certain points. So what's the point we took here? It's the we took the point of the bending moment, the maximum bending moments. The maximum bending moments on the system is at this point here, which is exactly at the depth F, at the depth 1.5d plus F from the ground level. So we have at this point, we have the maximum bending moments. So if we take the sum of moments at this point, we can take the top sections and we can take the bottom sections to find what's the value of the maximum bending moments on the systems. So if we took here the top sections, the above M maximum points, we have M maximum will be equivalent to the HU, which are, because we have here two forces, two horizontal forces above the M maximum, which are HU, the maximum lateral load on the pile, and the distributed forces. So this moment is coming from the lateral load. So now we need to multiply by the moment arm, and the moment arm here is equivalent to the, if we go back to this figure here, is equivalent to the E plus 1.5D plus F. So this is the moment arm of the force H. And then we need to find what's the moment arm of the distributed force on the top sections within the length F. And that will be F over 2, which is half of the length F. And that's what we have put here. So we have M maximum is equivalent to HU multiplied by the moment arm of the horizontal load. And that's minus because we took here the clockwise direction as positive. So that will be negative because this force will be rotating on the counterclockwise directions. If you go back here, H will rotate into clockwise directions about this point. But this force here, the resultant of this distributed force will rotate into counterclockwise. So that will be negative. That will be negative in this equation. So we have this equation here. If we substitute everything back into these equations and rearrange the equations, we're gonna get that M maximum will be equivalent to HU multiplied by E plus 1.5D plus 0.5 F. So this is from above the M maximum point. If we talk as well below the M maximum points, below the M maximum point, we have two distributed forces. As you can see here, we have this distributed force acting into that directions, and we have another distributed force, which is with the length G over 2, and this is with the length G over 2. So we need to find what's the moment from this distributed force and what's the moment from the distributed force, and equalizing that to M maximum, and that's below the maximum bending moment points. And what we got here, we got these equations. M maximum will be equivalent to 2.25 CUD G square. G is the length here. All these values G and F are length within the pile, within the length of the pile. They are part of the pile length. Okay, and Cu is the underend the shear strength, and D is the outside or the external diameter of the pile. And we do have another equation which is coming from the length of the pile. As we can see here, the length of the pile is equivalent to L, is equivalent to 1.5D plus F plus G. So this is another equations. And then if you put everything back into this equation, which is HU, this is equation number 1. If you substitute these values, because Cu is known value, D is known value. So if we put this one as 50 kilopascal and D as 0.305, then you're gonna get an equations which relate each u to the f value, to the length f value. Okay, and that will be each u equivalent to 137.25 f. And then if you combine equation 2 and 3, because these two equations, if you remember, they are the M maximum above the maximum bending point, and this is the below maximum bending moment point. So these equations, they are equivalent to each other. So if we put this term is equivalent to this term here by combining these two equations, 2 and 3, we're gonna have this equations. We're gonna call it equation number 6, and obviously after substituting the value of, instead of the value of f here in these equations, we're gonna substitute what we got from this equation, which is equation 1 or equation 5, we call it later. So we're gonna have here f is equivalent to HU divided by 137.25, and that's what we have done here. So we combine equation 2 and 3, and we substitute the value of f as HU divided by 137.25, and we end up with equation number 6 here. So now we have equation number 6, and we can have as well from equation number 4, if we substitute, instead of the value of f, we put HU divided by 137.25. So we got another equations here, which is equation number 7. And obviously after we put the values of L is equivalent to 6 meter. This is an input into this problem, into this questions. So we have the value of L as 6 meter. We have the value of D as 0.305. And then we put, instead of F, we put HU divided by 137.25. So we have another equations which relate G to the HU. And equation 6, if you remember here, it's HU as a function of G as well. So we have two equations with two variables, with two unknown variables, which are HU, the ultimate horizontal load, and the G value, the length G in the problem. So if we proceed with the solutions here, we need to substitute instead of G into this equations. So instead of G, we put here this value here from equation 7. By combining equation 7 and 6, we end up with one variable, which is HU, and then we can solve the problem by having one equation with one variable. So we end up with the maximum or the ultimate horizontal load in the problem is equivalent to 251.715. Okay, obviously you can follow this solutions or follow this method of solving the questions, okay, by deriving your basic equations. Remember, you have two equations from the static equilibrium. You have equations coming from the sum of the horizontal load in the problem, and equation coming from the sum of the moments on the system. So you can solve the questions by following this solutions, or you can go to the lecture notes. We have already derived the required equations to find the value of H ultimate and M maximum, depending on the static equilibrium principles. So as you can see here, we have followed the same principle here. This is the free head pile, short pile scenario, and this is the equations you need to use to find what's the value of H ultimate if you know the value of Cu, which is obviously given, and the value of D is given as well, the value of L is given in the problem, and the value of E is given in the problem. So you can use this equation directly, okay? Instead of deriving everything from the principle of static equilibrium, the sum of the forces in the system, the sum of moment on the systems, you can go directly to the lecture notes and use these equations to find what's the value of H ultimate by knowing the value of Cu, D, E, and L, okay? And you will get approximately the same answer because these equations, this equation here is derived from the static equilibrium principles of the horizontal forces in the system and the moments on the systems, okay? So after we have done from this part here, which is finding the ultimate horizontal load on the systems, we need to proceed with the solutions to find what's the value of F. We remember here, we relate F to the HU in this equation number 5. So we know that the value of F is equivalent to HU divided by 137.25. And that will give us what's the value of F in this problem. As you can see, it's 251.715, which is the value of HU in the problem, divided by 137.25, and that will give us 1.834, okay? And then you need to find what's the value of G, and the value of G, you can find it from this equation here, which is G is equivalent to 5.5425 minus F. We have already determined what's the value of F. Then we can substitute the value of F into this equation to find what's the value of G. After you find the value of G, you can use this equation here. You can use this equation here to find what's the value of M maximum in the problem. Because M maximum in the problem, you can either use these equations. You have already know what's the value of H ultimate, what's the value of E, what's the value of D, what's the value of F. You can either use these equations, okay, to find what's the value of M maximum, or use this equation to find what's the value of M maximum in the problem by knowing the value of F, D, and E, and knowing the value of G as well, D and C, you can find what's the value of M maximum in the problem. So we use the later equation, which is equation number 3 here, and we find the value of M maximum. The problem is equivalent to 2.25 multiplied by 50, the CU value multiplied by the diameter of the pipe, which is 0.305, multiplied by G square here in this problem, and we got the value of M maximum as 472.28 kilonewton meter. Instead of using this derivation as well, as we said, you can find the value of HU directly by using these equations. And as well, you can find the value of M maximum directly by using this equation here. You already got the value of H ultimate from the previous step or the previous equations, and you know the value of CU, you know the value of D, the value of E. You can use these equations to find out the value of M maximum in this problem, okay? And always it's a good practice to check the value of M maximum against the given M yield value for the pile material. Because for the short pile failure scenario, to be valid these assumptions, we need M maximum to be less than My, okay? So you need to check that is satisfied, because most of the case you will not be given which scenario you need to work out with. So you need to determine if your failure scenario is occurring according to the short pile failure scenario or according to the long pile failure scenario, and that's by comparing the determined M maximum value with the given My or the determined My value as well. So you can determine the M maximum by using these equations, and instead of working out the value of F and G, you can just work the value of HU from this equation. From this equation here, you can work out the value of H ultimate directly, okay? And after you work the value of H ultimate directly from these equations, you can go to these equations to determine what's the value of M maximum without working the value of F, G, and so on the lengths, because we have determined the lengths value here, F and G, just to determine the value of M maximum and to determine the value of HU. But that's, you need to determine these ones if you are working your solutions, okay, according to the static equilibrium principles here. But we have already derived the equation based on this principle. The analytical solutions for this scenario is already based on the static equilibrium. So we have already derived this one in these equations, okay? So we have done from this question here, which is question number 1. Now we haven't done yet. We need to determine what's the value of the stress in the problem. As you can see here, we need to determine what's the value of the maximum stress developed in the pile by assuming there is no axial load. So the only thing which left is the bending moments, which are gonna affect the maximum stress developed in the pile. So in this case, the maximum developed stress in the pile material will be equivalent to the maximum bending moments in maximum multiplied by the y, which is the moment arm until the midsections of the pile. Okay, so we need to work out what's the midsection of the pile material, which is half of the diameter here. Okay, and we need to work out what's the moment of inertia as well. The moment of inertia of the pile, because it's a circular cross section, it's a cylinder material. Okay, so we can use this equation here, which is y divided by 64, and that's between brackets 0.305, which is the external diameter to the power 4 minus internal diameter to the power 4. Okay, and to work out the internal diameter, it's the external diameter minus double of the thickness here, because you need to work out this inside diameter. So it will be the external diameter minus this length here minus that length here as well. Okay, so it's double of the thickness, d naught minus double of the thickness, or 2 times the thickness or the shear thickness of the pile material. So we have worked what's the value of I pile in this problem, and then if you substitute everything back into this equation, you can find what's the maximum double of the stress in the pile material. We need to substitute the value of M maximum, 472.28, and that's multiplied by the distance, half of the diameter of the pile, which is 0.305 divided by 2, and that's all divided by the moment of inertia of the pile material of the cylinder here, and that will give us that's the maximum stress developed is 411.56 megapascal here. Okay, so we have done this problem by using the equilibrium, static equilibrium principles, or you can use, as we said, you can use this equation directly. So instead of using the static equilibrium principle and the derived equations in your lecture notes, you can use the charts as well. We have here the charts. We have here 2 charts. This is the first chart here. And by using this chart, you can obtain directly what's the value of H ultimate divided by CU d square. And by finding this value, you're gonna find what's the value of H ultimate here. And to work out with this chart, it's much easier, it's much quicker as well. So if you have the options in the exam or in your when working with your assignments, you can using the chart instead of using equations and the static equilibrium, that will be much quicker, because to use this chart you only need the value of L over D, the length of the pile divided by diameter of the pile, and you need the value of eccentricity divided by the diameter of the pile. So these curves are for the eccentricity divided by the diameter, and the x-axis values are for the values of length divided by diameter. So by finding these 2 values, you can find the value of L over D and the value of E over D. You can work out what's the value of H over CUD square on the y-axis. And by doing so, you will find what's the value of H ultimate. And you can use another chart as well to find similar chart, to find what's the value of M maximum. By knowing the value of L over D and the value of E over D, you can find directly the value of M maximum on the y-axis after multiplying, obviously, by the 100 shear strength D cubic here. Okay, so if we're gonna use the chart, the value we're gonna get will be somehow different from the value we obtained using the equations. And the reason for that is because of the approximation on the chart, because everyone will approximate the value a bit differently. So if you use the chart here, we got the value of L over D 6 divided by 0.305, and that will be 19.672. We have the eccentricity over diameter as 0.5. That's the given eccentricity value, and diameter 0.305. We got 1.639. If we got these 2 values, if we take these 2 values, 19.6 and 1.6, in this chart first. So we have here 19.6 and 19.6 here, 19.6 and 1.6. So 19.6 will be somewhere here. It's closer to the 20. So we draw a vertical line until we hit the curve 1.62, 1.63, sorry, 1.63 here. So that will be out of the range because this range is up to this level. So as we can see, these two curves, the one drawn, the vertical line drawn from the x-axis, and the intersection with the curves here will be out of the range here. So we can extrapolate the value, do forward interpolations here to get what the value, to approximate what the value would be of h over COD square, and that will be somewhere here. They're gonna intersect somewhere here, and that will be approximately 55. You can maybe approximate that as 54, 56, 57, 53. That all will be correct because it's approximately correct. You are following the correct procedure here. So we're gonna get, by using the chart, different answer if we use the charts, because our approximation for this value will be different from 1 to 1. So here our approximation will be 55, and then you need to multiply by 55 by CU by D squared to get what's the value of HU. So as you can see, using the chart, this is the solutions for the problem. But by using the equations, we need maybe more workout. If you want to use the principle of the static equilibrium, that will take more time. And as you can see, the value of HU here from the chart will be 255. If we compare this value with the value obtained directly from the static equilibrium principle here, that will be 251. As you can see, there is a little difference here, about maybe 4 kilonewtons, and that's considerable here. So that's within the range of approximation, because all these values are approximated value. But this is the more accurate solutions because it's based on the analytical solution of the problem. So it's gonna be more accurate, but it's fine to use the chart as well because that will be much quicker. And for the value of mu, we have already derived the equations. If you remember here, we have already derived these equations here, which is M maximum is equivalent to HU multiplied by this value here. And we have already obtained this value here. So you can, after you obtained HU, you can get the value of M maximum directly. But if you haven't done that, but if you haven't obtained the value of F and G, obviously you cannot use this formula. So you can use another chart, this chart here, by knowing the value of L over D, the same as what we have done before with the previous chart. You can work out what's the value of intersections of the curve with the vertical line drawn from the x-axis, and you can work out what's the value of M maximum over CUD cubic, and that will be somewhere, because that will be 19, the line, they should intersect somewhere here, and that will be approximately maybe 340. So if you put here 340 into these equations, so to obtain the value of M maximum, you need to multiply 340 by the below term, which is CUD cubic. 50 multiplied by 0.305 to the power 3, that will give you the value of M maximum. Again, the value of obtained M maximum from the chart will be different from the value obtained from the equation here. It will be somehow different. After you obtain this value here, you need to obtain what's the value of stress within the pile material, and that's using the same equations as we used before, but different M value, different M maximum value, which is the one obtained from the charts, obviously. The same value of I, because I is independent of the method we are using. It's only dependent on the dimension of the pile here, of the pile material. And this is the midsections of the pile, which is diameter divided by 2. And as you can see, the solution as well is different because M maximum is different in both cases. In this case, we got 483. In the previous case, we got 472 kilonewton meter. Okay, so that's for the first questions. Okay, we have took more time because we have explained the three methods of finding H ultimate and M maximum, either from the first principle of static equilibrium by using the two equations the horizontal forces equations and the moments equations, or by using the equations derived in your lecture notes, obviously based on these principles as well, or by using the charts. So you have 3 options to use to find the value of H ultimate and the maximum in this problem. So after we have done from this question here, the first questions, we have only considered here the short pile failure scenario. We need to go to question 2. In question 2, if the yield moment of the steel is 430, we need to calculate the lateral load carrying capacity of the pile considering the long pile failure scenario. So we need now to consider the long pile failure scenario, and we need to consider that the yield moment is 430. Is 430 the yield moment? Obviously, we have from the first questions, so we need to use the same data from the first question. So question 2 is a continuity of question 1, but instead of using short pile failure scenario, as we said, we need to check against the value of in yield my. As you remember here, how to tell that we do have a short pile failure scenario or long pile failure scenario by comparing M maximum against My. So as you remember, the M maximum we obtained from the short pile failure scenario is either 472 or 483 using either methods, either the equations or the charts. So we got this value. This is the M maximum value. If you compare this value 483 by this value here, obviously the M maximum is more than the M yield. So in this scenario, for question 2 here, we do have the scenario as long pile failure scenario, So for this scenario, you can continue in the lecture slides, obviously. So for this scenario, as you can see, this is the My, because the ultimate load carrying capacity and the design values will depend on the My value, the M yield value. So you can use these equations to find what's the value of H ultimate. We have already been given the value of My as, in this case, as 430. So you need to have these equations. You have already been given the value of E and the value of D. So you're going to get a new equations with H ultimate and F value here. So in the second questions, as you can see, we got this value here, M maximum, which is equivalent to My in this case, because we need to equate these values to each other. And we end up with these equations, which relate HU to the F value. So that's equation number 1. And equation number 2, obviously, it's coming from the horizontal load equations. The horizontal load equations in the case of the long pile failure scenario, as you can see, this is the H, this is the long pile failure scenario for the free head pile systems. So we have only 2, because the failure will only occur here at this plastic hinge. It's not as the short pile failures scenario. So in the long pile failure scenario, the failure will occur at this point, or approximated at this point, which is at the depth of 1.5D plus F. So we have 2 horizontal forces in the system, which are the H ultimate and the distributed force above the maximum yield moment value here. So we have this horizontal force as 9 CUD multiplied by F. That will be equivalent to H here. So we got 2 equations, one coming from the sum of the moments and one coming from the sum of the horizontal forces. Okay, so you have 2 equations with 2 unknown values, which are HU and F. If you substitute one variable on the other formula, okay, you're gonna get the value of HU and the value of F, and by doing so, we're gonna get the value of HU as 236.42 kilo Newton. Okay, and that's by using the static equilibrium principles. Obviously, you can use the derived equations you can use the derived equation here for the long pile failure scenario. You can use this equation here because this equations, all the values are known values except the value of H ultimate. So you have the value of Cu as 50, you have the value of D as 0.305, you have the value of E as 0.5 meter, you have the value of My given as 430. So everything in this equation is given, so you can use it to find what's the value of H ultimate instead of deriving two equations and two unknown variables and then finding one unknown from the other unknown value by having one equations at the end. So you can use this derived equations directly to find your value, and obviously you can use this chart as well to find what's the value of H value by knowing the value of My, because we know the value. What's the value of My? 430 divided by 50 multiplied by 0.305 to the power 3. And we know the value of E as 0.5, the value of D as 0.305. So we know what's the value of the curve here. We know the value of the x-axis. We can work out what's the value of H ultimate, okay, directly from the chart. Okay, that's for the long pile failure scenario. So you have three options to find your H ultimate value, either in the short pile failure scenario or the long pile failure scenario. Okay, so that's for question 1 and 2. After we have done from the first two questions, the first two questions are for the free head piles. Free head pile. The third question will be for the fixed head pile scenario. So that's, we're gonna use other sets of equations, but it's still the same principle apply. You have three options to solve your problem, either by static equilibrium or the derived equation in your lecture notes or the charts in your lecture notes, okay? So we have here the length of the pile as 10 meter. It's embedded in a clay soil. It's a cohesive soil with a cohesion of 50 kilopascal. We need to calculate the horizontal load carrying capacity, H ultimate, and the moment capacity of the pile in maximum of the pile, considering three failure modes, short, intermediate, and long, because here we have fixed. So in the fixed, we do have three failure modes, but in the free, we have two failure modes, short and long. But in here, we're gonna have short, intermediate, and long because it's a fixed head pile scenario. We need to assume that the yield moment of the steel pile is 450 kilonewton meter, and the diameter is 0.4 meter, and the wall thickness is 12 millimeter. Okay, so we got here the value of the yield moment, we got the value of diameter, we got the value of the wall thickness as well. So we're gonna proceed with the solutions. Okay, but before proceeding with the solutions, we need to go to the lecture notes to see where are the equations. So this is the fixed head pile in cohesive soil. So as you can see, we have three failure modes, short, intermediate, and long here. The first one, you have in each slide, you have the derived equations based on the failure scenario. So this is the fixed head pile for the short pile. We need to assume this short head pile. And as you can see, this is the sum of the horizontal forces will give us what's the value of H ultimate or H limit, okay? And the ultimate value here, as we can see, it's by using the horizontal, the sum of the horizontal forces on the system. H ultimate will be equivalent to the resultant force from the distributed force here, the reaction from the soil, which is 9 CUD multiplied by the length of the distributed force here along the pile, which is L minus 1.5D. So 9 CUD multiplied by L1 minus 5D will give us what's the value of H ultimate. And if you go back to this question here, the value of L is given, the value of Cu is given, the value of diameter is given. So everything is given in these equations. So we can use this equation directly to find what's the value of what's the value of H ultimate. And that's what we have done here. We have the value of H ultimate as 9 CUD multiplied by L minus 1.5D. We put everything into equations. We put what's the value of H ultimate directly by using this derived equations. This derived equation, and this is the same as the one we derived from the static equilibrium principle directly, which is because we have only two horizontal forces, the H ultimate acting at the top of the pipe, and the reaction from the soil here, which is approximated as 9 CUD multiplied by this length, where this length here is L minus 1.5D. And the sum of the moment, because we have here two forces in the system, we can take the sum of the moments, and that will give us this equation here. M maximum is equivalent to the H ultimate we have determined here. That's multiplied by 0.5 L is given, and plus 0.75 D. The derivation of this equation is already given in the solution here, how we derive these equations. And this is the M ultimate or the M maximum value, and all the values are given here. So it's much easier than the previous questions, or it's more straightforward. We got the value of mu as 8,967.6 kilonewton meter. That's the mu value. And now for the intermediate failure scenario. For the intermediate failure scenario, we have the same set of questions. So if you proceed with the, and obviously you can use as well the charts to find what's the value of, instead of using this equation, but obviously it's much easier to use these equations. But you can as well, you have the option to use this chart to find what's the value of H for the fixed head short pile in cohesive soil. You can find this, you can use this chart as well to find what's the value of M maximum, but we need to check always for M maximum if it's lower or higher than the MY, if the short pile failure scenario prevail, or the long or the intermediates. Now, if we proceed with the intermediate, we need to consider the MY into considerations here. And this is the distribution of the forces here. The sum of the horizontal force will be the same, which is the horizontal H ultimate will be equivalent to this section only, because these two sections will cancel each other because they're acting against each other. So we only have this portion here, and that will be equivalent to the H ultimate here. And from this, if we proceed with the derivations, we're gonna have this formula here for the H ultimate will be equivalent to Cu d square. Cu is given, d is given, L is given in the questions, mu is given. So we can use this equation to find what's the value of H ultimate directly, okay, without going into the derivations based on the static equilibrium principle. But obviously you can use that principle as well. It's already given as we explained in the first questions. Or you can use this chart to find what's the value of H ultimate in the case of intermediate fixed head piles in cohesive soil by knowing what's the value of L over T and what are the value of intermediate if my CUD cubic value. So you need to use this curved line, because this one, the straight lines are for the long pile failure scenario. So this chart, you can use it for either short pile or intermediate pile or long pile failure scenario, because that will be governed by the value of my here. You can determine what's the value, what's the corresponding value of H ultimate on the y-axis. So you can use this value here, obviously. But in here we have used the static equilibrium principles by having these equations from the equilibrium of the horizontal forces on the system. As we said, we have H ultimate is equivalent to the 9 CUD multiplied by F here, which is the one here, if we go back, which is this portion here, F multiplied by 9 CUD is equivalent to H ultimate. And we have another equation from the length of the pile. Length of the pile is equivalent to 1.5D plus F plus G. So we have here two equations. And then we're gonna have another equations by from the moments, from the equilibrium of moments on the system. And yield will be equivalent to this formula here. You can derive it yourself here, but it's based on the on these forces. It's based on these forces here by taking the moments my at this point here at the plastic hinge point, the rotational point or the fixing point if we take the moments at the ground level. Okay, if we take the moment at the ground level, then we need to find what's the sum of the moments on the system. We're gonna have my, we're gonna have this force here, we're gonna have this force here, we're gonna have 3 distributed forces. You need to find what's the moment R of each force multiplied by the resultant force from each distributed force by its moment R, according or up to the ground level. Okay, and that will give you this equation here. It's the same derivation. Will give you equation number 3, and then if you proceed with the solutions, you're going to have equation number 4, and equation number 4 is only a function of f and g here, and we have another equation which is a function of f and g here as well, because L is given here. So if we solve these 2 equations, we're gonna find what's the value of f, okay, because you have these equations, okay, equation number 4 as a function of f and g, and you have this equation number 2 as a function of f and g, because L is given as 10 meter. So we can use these 2 equations with 2 unknowns to find what's the value of f in the problem. After we find what's the value of f, we can obviously determine what's the value of h ultimate in the system here. And that's what we have done here. We have defined, determine what's the value of f, and then we determine what's the value of h ultimate. And m ultimate on the system is equivalent to m yield, because we are dealing with intermediate fixed pile failure scenario. So the m maximum will be equivalent to m yield scenario, because we cannot exceed the m yield value in the intermediate and the long pile failure scenario. And the last one to solve here is the one coming from the long pile failure scenario. And again, you can use the static equilibrium principles, or you can use the derived equations. The derived equation here, which is H is equivalent to 9 CUD F, and then you can relate this one here, considering moment arm of the pile about lower hinge between 2 plastic hinge. We're gonna end up with this equation here, which is as a function of F and my. If we substitute the value of F here from this equation, we're gonna end up with this equation here, which is relating H ultimate to the CU, the given value, D is given value, MU is given value. So MU is given value, CU given, D is given. You can find what's the H ultimate value directly from these equations, okay, under the long pile failure scenario, under the fixed long pile failure scenario. And obviously you can use these equations to find what's the value, but now you need to use the straight lines to find what's the value of H over CUD square, okay? And so this is for these questions. So in here we have derived these equations. We find what's the value of HU depending on the static equilibrium principles by finding 2 systems of equations. One according to the sum of the horizontal forces of the systems, and the other according to the sum of moments on the system. So I want you to try the 3 different methods, and to compare the results from each method, and to practice these methods. So at the time of exam or while working in your design projects, you will find this equation handy. Okay. So we have done from the first 3 questions. We only have 5 minutes. So if you do have any questions, I will be happy to answer your questions. And if we're gonna have a time next week, we're gonna do question 4 and 5. Question 4 and 5, they are based on the same principle, but instead of having cohesive soil, we're gonna have cohesionless soil. So the principle is still the same. It's the static equilibrium principle, but we're gonna have other sets of equations, because now the reaction from the cohesionless soil will be different from the reaction from the cohesive soil. So that's the only difference from the cohesionless soil and the cohesive soil. So please, if you do have any question, you can ask me on the chat, and I will be happy to answer your queries. The tutorial is already recorded, so it will be uploaded shortly after the tutorial time. maybe sometime tonight. I'll upload the video for this tutorial. And at 1 o'clock, we're gonna have the computer lab, the last computer lab in this semester. And it will be an extension of lab 3 and lab 4, which is using RS3 for axial load, combined loading. And today we're gonna have bending moments as well. We're gonna incorporate the bending moment into our modeling. So we're gonna see how to incorporate the bending moments into the model, and how we're gonna analyze the results after we model our problem. Okay, so I thank all of you for joining me today, and I will see you at 1 o'clock at the computer lab. Thank you, everyone.